so good at pretending. Keep on smiling in my tiny bubble, like a movie without ending. Spending time like it was going backwards. Bruises covering my walls, but they fall down. Diving deeper in the books that we read blind. Breathing in and breathing out to get smarter. Not working out for me, yeah. Got no money on my mind. Tell my mommy I'm alright. Even laughing at the jokes you tell me. Keep myself inside the lines. Neat and tidy all the time. If you ask me, I am fine. Got no money on my mind. Repeating patterns like the others. Meditation through the yoga lessons. Going greener by the minute. Soon I can't wear any other colors. Bruises covering my walls, but they fall down. Diving deeper in the books that we read blind. Breathing in and breathing out to get smarter. Not working out for me, yeah. Got no money on my mind. Tell my mommy I'm alright. Even laughing at the jokes you tell me. Keep myself inside the lines. Neat and tidy all the time. If you ask me, I am fine. Got no money on my mind. Don't you worry about me. If I keep feeling like
Hey robot makers, how are you doing? Hope you're having a good weekend so far. So, have you heard about easing and motion transitions for servos? So that's what today's show is going to be all about, and we're going to be using the Raspberry Pi Pico and MicroPython, and we're going to be putting all this into OpenCat later on. So let's do this. So I'm going to go over to the keynote that I've got ready for you guys. Oops, showing you all the good stuff already there. So yes, the goals of this session today is we're going to create a new leg class in our MicroPython code that we created last week. We're going to add some servos to that leg class, a foot and a leg. And we are going to add those legs, 4 of them, non-surprisingly, to our PicoCat. And then we're going to understand about how transitions work and smoothing. This is really cool stuff. It's simpler than you think, but also more complicated than you think at the same time. I was never good at quadratic equations when I was in school, and apparently this is what these are, but they're just code. As far as I'm concerned, 4 parameters, and it makes a load of sense. So let's get to this. So what is easing? So you can see on this little animation I put together here, the limb on the left has no easing at all, and you can see it's just rotating at a constant rate, and it doesn't look very natural at all. It looks very unnatural, in fact. So look at the one on the right, which has some easing. It sort of slows down, speeds up in the middle, and then slows down again. That's much more like a natural kind of muscle movement. So we want to make our cat as natural as possible, and this kind of easing will also help just bring it to life in a better way than if it was just without easing. So it does introduce a little complexity, but we can hide that with code, and we can write it once and we can use it everywhere. So we can use it in our auto, because that has servos. We can use it in our quad, which I've got 3 behind me over there. And you can also see the 2 limbs there for the in move. So he has loads of servos in him, and of course we can use it in that too. So this is what we're going to do. So linear transition. So if we don't have any smoothing at all on there, what does that actually look like? So if we have a look at that as a graph, I'm sure you all enjoy graphs as much as I do. So if we have time across the bottom, and we have whatever the value is, whatever it's going from and to as an angle, is the sort of axis there, the y-axis. So the transition duration is just the time, and how the value changes over that time is exactly linear. So it starts up and it's just a 45-degree kind of angle. Nothing interesting going on there. So that's without. Now, with easing, we have a curve. So on this particular one, this is a circular easing in transition, and the amount of the value changes slowly at first and then accelerates towards the end. So that will give us that much more natural kind of look to it, if that's the particular transition that we're interested in. So that's easing in. Now there's another type which is easing out. So the amount of the value starts quickly and then slows down towards the end. So it kind of decelerates. Now it might be that we want to pair both of these up, and that's called an in-out, non-surprisingly. I always think this is called an S-curve because it's kind of like an elongated S. So the amount starts slow, accelerates in the middle, and then slows off towards the end. And that's similar to the one in the animation that we had just at the beginning of the show there. And there are different types of algorithm that we can use, all different types, and they give you a more harsh or more softer kind of transition. So we've just seen the linear tween. A tween is kind of a between spline. Don't have to worry about these kind of terms at this point. So linear just means we don't have any kind of transition, any kind of smoothing at all. Circular, cubic, exponential, quadratic, quartic, and quintic, and sinusoidal are all different types, and we'll see when we get into the code of some of these what they actually mean. So the quadratic, quartic, and quintic are basically 4, 5, and 6 multiplications of the value inside. So we're going to look at the sinusoidal one in some of our code today. Rather than going through over every single one of them, we'd be here all evening if we did that. So I'm just going to pick one or two of these so we can have a look at that and how that works in the code. So here's all the different types of graph laid out. Now that might be a little bit small. Let's see if we can make that any bigger. There we go. Got my face in there though. I can switch between sides if we need to. So yeah, on the first sort of column we've got circular. So these are quite an intermediate. If you look at all the different curves of the, from the flattest ones like cubic and sine to the exponential and quint, which are much more extreme versions of the curve. Circular is kind of somewhere in between there. Cubic is quite flat. If you look at the sine wave, that's quite similar. Exponential and quint, quart and quad kind of back off. I really should have moved the exponential maybe towards the very end because we use power to figure that one out. We've got the ease in row, the ease out row, and the ease in out row. So we might decide that for certain types of motion we would only pick an ease in or out, but I would probably guess that for most things we're going to use an ease in out. Or if you've ever done any animation, character animation in something like After Effects, they call that an ease because it just picks the two things for you, the ease in and out. And I think they go for something similar to like a sine. It's quite a gentle one. So depending on how we want this motion to look, do we want something as extreme as the sort of exponential one where it's very severe in and out? Or do we want something that's much, much smoother like the sine one? If I just move out the way on that one. Yep. You can see there the sine is much smoother. So they're the different types. You don't have to memorize these. We can put them into code. Just be aware that there is an in and out and an in and out and in out for each of them. And there is, 7 different curves there that we can use. This isn't the limit. There's loads of other ones. There are some which actually go past the bounds and create like a bounce effect. That's quite a common one. So if there is quite a few really cool websites. Stretching really cool. Depends if you're into this kind of thing or not. If you look online and look for easing, there are at least 3 or 4 websites that have these graphs on that have the code in Python or other languages as well. I had to test some of these out and I got some of them wrong to begin with because I was trying to convert between C and Python, and there's a few quirks there with that, but I've got the sine one working perfectly today, so I was very pleased with that. So let me just put me over there for a second. So how do we actually add these things to our code? Because it's all very well saying curves and graphs and things, and we've seen how that actually works in reality, but what does this mean from a code point of view? So it's going to be a function, and it takes 4 parameters, and this is pretty standard across all the easing functions that I've come across so far. They always take the same 4 parameters. So they take the current time. So at some point we're going to say start the transition now, and then we're going to have a clock ticking, and that clock ticking is the current time. It's whatever we're coming at this algorithm with, and we'll run this algorithm many times to get the different values over that time. The start value is where in our case, it's going to be servos with an angle. So we might not start at 0, we might start at 90 or 45 degrees or whatever the previous or current value of that angle is. So start value is the angle that we're starting from. The change in value is the end angle minus the start value. So this is where I got messed up when I was trying this out yesterday. And I'll come to that in a second. And the duration is just how long this thing's going to take. So if we have like a 2-second transition, the duration is going to be 2 seconds, but we'll actually express it in microseconds, so it'll be like 2 million. So the reason I said I messed this up, and I'll come back to this, yes, this was not straightforward when I was looking at this earlier, and I like to try and all the code I'm going to show you today as a kind of speed run, so there is no mistakes in what I deliver, but sometimes that will happen, but I try and minimize it a bit, so I'm not just sort of sat there for hours going, what does this mean? I want to just give you the facts straight away. So just be aware that I spend all my Saturdays just hacking the code to pieces and trying to make this thing figure out. So yeah, so Skinnyfish says, I managed to get 3 of these bad boys from Pimeroni, looking forward to tinkering. Absolutely. So like yourself, I've got quite a number of these things from Pimeroni. I think got one from Pi Hut. Where's my Pi Hut one? I think it's downstairs still in the house. And I've got a very sad story to tell you about one of them as well. I'll tell you that after we've gone through this little slide deck. So that's what we need to do. We've got these 4 parameters. So the current time is the elapsed time in microseconds. The start time there is the start angle, e.g. 90 degrees. The change in value is the target angle minus the starting angle. That's just something we need to be aware of, and we can put that in our code. And the duration is just how long it will take in microseconds. So the easing function will return the value that the angle should be set to, so what the servo should be set to. So when we run this transition, it will return a value, and that's what we're going to use to set our angle. And we'll run it in a loop, and we can either run it for the duration, or we can run it until it's reached the angle. We can do either of those 2 things. Okay. So an easing loop. So this is not like a set and forget or set and sleep like we did before in our code, where we would simply just say, here's the pulse width for the particular servo, go and set that, and then we will say, let's wait for, I don't know, 1/10 of a second while the physical servo will energize up its little motor inside. It'll turn until it gets to the correct position, and there's like a little potentiometer in there that will wait until it gets to that correct value, and then it will stop. So those things take time to do, and that's normally where the sleep function comes in. So we're going to do things a little bit differently now in this loop, because we're going to actually run that algorithm many times over so that this thing can actually have this motion, because it will look smooth, but actually what's happening is it's being run lots of times, and depending where on the algorithm it is, where on that curve it is, it will set the angle of the servo. So we need to evaluate this loop, evaluate these 4 parameters that are passed in for the duration of the transition. So we can see there we've got some pseudo code. Again, should we just try and zoom in a little bit on this? So while elapsed time in seconds is less than the duration in seconds, then we need to set the current time to, and we need something to give us a slice of time. So in MicroPython there is a time function, and within the time library there is something called ticks US, and the US is the give it to me in microseconds. You can have milliseconds or microseconds. I just chose microseconds for this. There's probably pros and cons for doing either, but that's just what I picked. And then what we do is we say, right, the current angle that we're interested in is equal to, and then we run this transition code. So, and we'll actually look inside what that is and put that into our code in a second. So don't worry about what that does. It just takes those 4 parameters. So we're going to use the ease in sign type of transition. We're going to say the current time is equal to the self.elapsed time, which is what we're going to grab in a minute. We're going to say the start value is whatever we want the start angle to be within our class. The change in value is going to be whatever we've set to the change in value, and the duration is what we've set to be the duration in our class. And then after it's given us that value back into the current angle, we then say set our angle to that current angle. So that's what we need to do. And depending on which type of transition that we're going to use, we might have several blocks of code. So when I'm creating this, I've got two Python scripts. I've got one that's called PicoCat, and that's the one that we're currently working on as we go through this series. And there's one that's called OpenCat, and that's the one that I'm kind of working ahead, at least one episode ahead in there. And that's probably got lots of things that I've tried that didn't work as well. So I've got my iPad next to me here as well, so I can just refer to that as we go. Okay, so if you're enjoying this series so far, really, oops, we don't want the comment of the week, we want that one. So yes, I'd rather like it if you can like, subscribe, and drop a comment. If you tick the little bell as well on YouTube, you'll also get notified if any new episodes land. And I tend to do 2 a week. So we have the Sunday night live stream, and we also have, that's a really funny camera angle, that. And we have the, let me go back to that one there. Oh, it's locked. Hang on. There we go. Yes, we have the one midweek as well, which tends to be like a pre-recorded one, depending on how much time I've got in the week to spend doing this, and also if there's something that's interesting for you guys to watch. Cool. So that's that. Let me have a look what else we have on our KeyNote. So demo time. So before we get to the demo, I want to share with you this story about what happened with my poor old Raspberry Pi Pico. So let me just show you on the overhead. I've got my desk a bit of a mess at the moment because I'm working on 2 cats. I've got the one that I built previously, and then there's this orange and red one which I'm currently in the middle of building. It's a slightly different model. This one has slightly different feet and doesn't require any screws. Everything sort of just fits together, whereas the one I've built previously has lots of screws in it. So just trying out a different design. So anyway, this is the sad story. So let me just bring up this, and let me just bring up. So yeah, what happened? This is my Raspberry Pi Pico, the first one I soldered some legs to. And I had this wired up to this board that's just here. In fact, these are the 2 incriminating pins that did the damage. So I had these wired up to, I think it was these pins here, 1 and 2. It's either them there or them there. And I also was powering 11 servos using this PCA 9685 board through the Pico. Now, given that this Pico is only, what, 3.3 volts, that was probably far too much current going through this poor thing. So there was some strange smoke that appeared coming from this thing here, and yeah, that smelled horrible. And then this thing went offline, and when I plugged it in, it's not worked since. So yeah, cost £3. It's not the end of the world, is it really? But it's a lesson not to try and power things through these tiny little boards. The thing is, this PCA 9685 board has separate inputs for power, and I have a desk power supply just off camera here, so there's no real reason why I should have done that. I was just trying to make the whole thing work. So yes, let me set the camera back to what it should be as well. So I thought I'd share that with you. Oops, wrong button there. So yeah, I thought I'd share that with you. Sometimes these things happen, we end up damaging boards. Luckily, these things are quite cheap. They are like rocking horse poop to try and get hold of at the moment, though. They're not very easy to find. But I did order a few of them, so I've got a few spares just in case. Talking about cases, the midweek video that I put out last week was how to design a case for your Raspberry Pi Pico. So you can see there, this is sort of inspired by the Raspberry Pi Zero, which is there. So the Pico has now got a little case all of its own, which is very similar to that. So if you're interested in that video, that's out there, showing you how to use Fusion 360 to do that. It's quite interesting because it has some nice swooping lofts on it. These curved edges are called lofts when you do it in Fusion 360. So that's worth a watch if you've not seen that already. Okay, so we get over to some code. That's what you're all waiting for. So let me press the right button there. So we need to get over to to here. So this is the code that we created last week. So you can see there we had the servo class, which is quite lightweight, quite a few properties in there to set. So we have a property that returns a value, we have the setter which will set the value, and then we've down at the bottom there we just have a bit of test code. So we've said s equals servo, and then we just try some values out to make the neck move. So what we've not created in there is the actual PicoCat itself. So we can do that this week, and we can also create a couple of other classes as well. So there's a leg class that we need to create, as well as a transition class. So let's get to it. So the first one that we'll create, how should we do this? Let's have a think. The transition one might be an interesting one to do first. So let me just get that open on my other screen that I've got just off camera here. There we go. Right, so let's go over to here. Let's create a new file, and we'll call this one transition.py. Okay, and this is going to, first of all, import that math function that we need. So from math, import, and we need sine, because we're going to be doing some stuff with curves, cosine, pi, and square root, which is those four. So this is what's quite interesting about the MicroPython. It has got quite a few libraries that are standard from Python, and the maths library is one of them. So you don't need a file to import there, but you do need to tell it which libraries you need to import. And the reason we do from the library rather than just saying import math, import everything, is because the Pico has got a limited amount of memory that's in there. So the more that we limit down what we want to load in, the more memory we'll have available for everything else. So let's create a class. We'll call this one transition. Our classes always have a capital letter. That's the way. That is the way. And what we'll do, we'll pick the ease in sine. So let me just find that one on my iPad. I've got all the algorithms. I spent all of Saturday typing out all of those different things. What was the 7 or 8, 3 rows? Yeah, it's about 21 different algorithm things I had to type in. So what we need to do then is we need to say, I'm going to do it like this. I'm going to say calculate rather than just return, but we could just return the value and have the calculation in there. So what we're going to say is 1 minus, oh, before we do that actually, what we need to do, sorry, is we need to define the ease in sine. Yes, and let's just close that so we've got a bit more space there. Okay, and we need 4 parameters. If you remember, we need to have, well, we always need to have self, so we ignore that one. That's just so that because it's a class, you always have to include self, so it can refer back to itself as an instance. So current time, start value, change in value, and duration. They're the 4 parameters that we need to have. And we're going to do this thing, like I said, calc. And what we're going to calculate, so 1 minus change in value. And that's going to times by cosine. And that's going to have the current time divided by the duration. Times by, and this is where the curve bit comes in, pi divided by 2, and then we're going to add to that the change in value plus the start value. So there's a lot going on there. To a degree, you just have to trust that this works, and if it doesn't work, you probably need to sit down and think about why does that not work. But these algorithms are quite standard, as in you can pick up this code that works exactly the same way. They sometimes just have letters rather than the full word spelled out, but I think having the word spelled out just makes it easier for you to understand what's going on here. So we can take a quick rough guess at this. So what we're saying is, and sometimes you have to kind of work backwards from this, or work from within the brackets to figure out what's going on. So what we're going to do is we're going to start out with a value of 1. We're then going to take from that the change in value, and that could be a value between whatever the angle is currently and what we want it to be. It's going to then multiply that by cosine, which is another maths function usually used for triangles and waveforms and things like that. And then because that's a function, that takes a parameter as well, and what we're going to give it is whatever the current time is, so how many seconds have elapsed, microseconds have elapsed, divided by the total duration, and then it's going to times that by pi, and that will give us the curve. That